Okay, thank you for being here. This is joint work with Xiaosheng. All right, so we study a social learning model where agents have access to a large number of different kinds of information, and they sequentially choose between them. Okay, so for this talk, I'm going to keep as the main example medical researchers studying something like depression, and they have a large set of different neurochemical or genetic measurements that they could be taking, and they're choosing which ones to acquire. Okay, you can also think about a company that's training some sort of predictive algorithm, and each period it's actively choosing to acquire new data points for this training. Okay. Now, the kinds of data that we have in mind are related in potentially complex ways. For example, some kinds of information may be complementary. Is that my phone, actually? I think it is. Thank you, Hongkai. Thanks, Hongkai. Great. Okay, so some kinds of data may be complementary. And what that means is that a given agent's choice of information has externalities for other agents, in particular by shaping their perception of what information is most valuable. So what we do is we propose a model with these features, and then we characterize long-run information acquisitions. Okay, I'm going to show you that there's two different outcomes that can arise in the long run. So in one class of informational environments, we get efficient information aggregation. Okay, so what that means is that even though these agents are acquiring information from a more short-sighted perspective, they're nevertheless going to acquire information that is going to allow the community or the company to learn as fast as possible. In the other outcome, we have what we're calling learning traps. So agents are acquiring information from sources that are actually suboptimal, and they're learning inefficiently slowly, even though there are these better sources out there. And now, which of these obtains is going to depend on the whole set of relationships across the sources, and our main results identify a simple property on the correlation structure that is going to allow us to classify cases into efficient information aggregation or learning traps. Okay, so without further ado, here's the model, and if you were here for the first part of this session, then some of this is going to be a reminder. Okay, so there's k unknown states. One of these states is special, it's this blue omega. Okay, that state is payoff relevant. In addition, there are k-1 payoff irrelevant states. You can think about these as confounding terms or as biases. Throughout, I'm going to use theta to denote the whole state vector, and I'm going to assume that it is jointly normal. Okay, now, agents have access to n different sources or kinds of information. Each kind of information is modeled as a linear combination of the unknown states, plus an independent Gaussian noise term. So here, Ci is a coefficient vector that is special to source I. Theta is the state vector from above. Okay. These errors are IAD across time and also sources. You might notice that I've normalized the error term. That is actually without loss of generality because we haven't restricted the size of the coefficients. Okay, so we can have sources that differ in this vertical dimension of precision in addition to this horizontal dimension of kind. And then relative to the earlier talk, the key difference here is that n can be significantly larger than k, and I'm going to say a little bit more on this in a moment. All right, so that's the informational environment. The decision environment is as follows. We have agents who are indexed by discrete time. Each agent is going to do two things. So first, he's going to choose one of these n different sources and observe a signal realization. After that, he's going to predict this payoff relevant state, omega, and his payoff is going to be given by the following, where AT is his prediction. Okay, throughout, we're going to assume that all signal realizations are public. So in the researcher setting, this is like you can see the whole canon of everything that's been written in the past. Okay. So what that implies is that these agents are going to be choosing which signal to acquire, and also basing their prediction off of the entire history of signal acquisitions and signal realizations. Okay, this is a key departure from the herding literature if you are familiar with it. All right, so just to give you a concrete example of what an informational environment might look like, here we have three different signals. Okay, so x1 here is a confounded signal about the payoff relevant state. So you've got 5 times omega, which is payoff relevant, plus b1, this confounding term. X2 is a signal that's actually not directly about the payoff relevant state. Instead, it's about this confounding term b1. Okay, it can nevertheless be useful to you, either because b1 is correlated with omega, or because observations of x2 help you to interpret the realizations of x1 and to debias. Okay, then finally, we have x3, which is an unbiased signal about the payoff relevant state. Now, what's interesting about this setting, and we're going to refer to this as a setting of informational overabundance. If you look at the first two signals, x1 and x2, it is possible to recover omega by exclusively and repeatedly observing these two signals alone. Okay, the easiest way to see that is that x1 minus x2 is an unbiased signal about omega. So we're going to refer to that as a spanning set. Okay, and moreover, I'm actually going to call this a minimal spanning set because it's not possible to recover omega if you throw out either x1 or x2. And what's interesting about this example is that, yes, that's a minimal spanning set, but it's not the only minimal spanning set. So for example, x3 here is another minimal spanning set. And this is exactly what I'm going to mean by informational overabundance. There are these many different channels for learning about omega, and hence we can ask how will agents in fact end up learning about omega. Okay, this is also the key difference from the previous paper in which we assumed that everything was exactly identified. Okay, so we're interested in society's acquisitions, and hence we're going to track their acquisitions using the following count vectors. So here Q of t is an n by 1 vector, where each coordinate Qi of t is the number of times that signal I has been acquired by time t. So initially, we have counts of 0 for all of the signals. Okay, perhaps x1 is acquired first. I'm also keeping track of a normalized frequency vector. Perhaps x2 is acquired next. And in general, we have these counts. We are interested in these long-run frequency vectors. So this is the fraction of periods that are devoted to each signal as we take the whole number of periods to be large. Okay, so this is the key object of the analysis. Okay, and just to give you a preview of our results, again, using this example, the first question we ask is, how should the signals be viewed? And so if we were to take an optimal sampling procedure, what would be the long-run frequencies corresponding to that? In this example, it turns out that the optimal thing to do is, in the long run, not observe x3 at all, and to devote your attention equally between x1 and x2. And then we can ask, how will agents actually end up acquiring information? And we can compare their signal acquisitions to this optimal benchmark. Okay, and it turns out that sometimes agents acquire signals in a way that converges to this optimal long-run frequency. And that's what we're going to call efficient information aggregation. Okay, in other cases, the long-run frequency can look quite different, and these are the cases we will think of as learning traps. All right, so without further ado, let me tell you about this optimal benchmark. So we take two different perspectives on what it means for a sampling procedure to be optimal. Okay, so one perspective is purely in terms of information revelation. We ask which signal acquisitions would maximize long-run speed of learning about the payoff relevant state omega. Okay, the other criterion we look at is more of a social planner criterion. So we say, consider a social planner that cares about all of the agents, and he's going to maximize a discounted aggregate of the different payoffs that the different agents are receiving. Okay, here we're going to consider a patient limit corresponding to taking delta towards 1. Okay, these two different perspectives end up yielding the same long-run frequencies, and that's what I'm going to refer to as the optimal long-run frequencies. Right. Now, what's tricky about this problem is we don't even know the support of the optimal long-run frequency. Right? So exactly because there are these many different ways to learn about omega, there's many different signals that could conceivably receive 0 long-run frequency. Now, this is much simpler if instead what we have is a setting of exact identification where you have to observe all of the signals in order to recover omega. So let's just start by considering the simpler case where the available signals is itself a minimal spanning set. In this case, we can write the first coordinate vector, E1, as a linear combination of the coefficient vectors associated with the signals in that set. Right, so here, for example, the two coefficient vectors are C1 and C2. And we can write this first coordinate vector as 1/5 times C1 minus 1/5 times C2. So in this example, beta 1 is 1/5, and beta 2 is negative 1/5. So it turns out these coefficients are intimately related to the optimal sampling procedure. Okay, so first, the long-run frequency of observation of signal I under optimal sampling is proportional to the absolute value of the coefficient beta I. Okay, so the larger your beta I is, the more frequently you should be observed. And in this example, what that means is that these two signals should be observed with equal proportion. Okay. We can also show that the posterior variance under optimal sampling from this set is going to tend towards the following expression. Okay, where phi of s, you can think about this as an asymptotic standard deviation. That is equal to the sum of the absolute values of these beta coefficients. So in this example, phi of s is equal to 2/5. And what this allows us to do is to compare the different possible minimal spanning sets. So we can apply this result minimal spanning set by minimal spanning set, find their phi values. The smaller phi is, the better. And throughout, I'm going to impose this assumption, which is generically satisfied. It says that phi has a unique minimizer among all of the minimal spanning sets. I'm going to call that unique minimizer S star. So that is a best minimal spanning set. In this example that's satisfied, we have the two minimal spanning sets, recall. The first one has a phi value of 2/5, and the second one has a phi value of 1. So what that means is that the first set is the better minimal spanning set. Okay. So now, if I were to restrict the agents to acquiring information exclusively from some minimal spanning set, then the solution is straightforward. Okay, we know that x1, x2 is best, so let's assign frequency 0 to x3 and then sample from x1 and x2 according to this first bullet here. Okay. But in principle, with flexible sampling rules, you could actually combine the signals from different minimal spanning sets. And our first main result says, in fact, you can't improve in that manner. So this strategy that I've just shown you is actually the best long-run frequency under arbitrary sampling procedures. Okay, so that's exactly what this theorem says. Lambda I star here assigns 0 frequency to all signals outside of S star, and then within S star, it samples signals in proportion to their beta I values. Okay. So now with this in hand, we can turn to the actual social acquisitions. Again, recall our purpose in having this is to have this benchmark for making welfare comparisons. Right. So let me first convince you that society need not converge to those optimal frequencies that we were just looking at. Right, so consider this example that we've been talking about. We just saw that the set x1, x2 is best in the sense that a social planner would want agents to eventually be observing just those two signals. But consider a prior belief where omega and B1 are initially independent, and you have a lot of uncertainty about B1. Okay. Now consider the first agent. He's going to look at x1 and perceive x1 to be this very noisy signal about omega. Okay. He's going to look at x2 and perceive x2 to essentially be this irrelevant signal, because it's about this confounding term that's not even related to omega, and hence he's going to acquire signal x3. Now, because omega and B1 are independent, this doesn't teach the next agent anything about B1. So actually, iterating the same logic, every single agent is going to acquire x3. And we see here, what this means is it's not just that society is not going to converge to the optimal frequencies, but in fact, the set of signals that they observe in the long run can be disjoint from the optimal set. And again, going back to the researcher example, you might interpret x3 as exploiting some existing technology for learning about depression. Okay? And perhaps there's some new imaging technology that's out there, but it's extremely poor. And you can think about x2 as advancing this new imaging technology, and x1 as exploiting this imaging technology. So what society would really like is for somebody to be investing in this confounding term B1, but each agent doesn't want to be the one to do that himself. Was that a time 5 or was that a question? Okay, thanks. All right. And our first result, main result here, generalizes that phenomenon. It says that for every minimal spanning set that contains strictly fewer than capital K signals, there is some open set of prior beliefs given which that set is exclusively observed in the long run. Okay, so this is a general condition under which we can get learning traps like x3 in this example. Okay. Our next result says, so here we know that if it is possible to learn omega from fewer than capital K signals, we can get learning traps. The next result says that if instead, you have to observe some capital K signals in order to recover omega, then we get the opposite outcome. Okay, so if every minimal spanning set is of size capital K, then QIT, these are the society's counts, those are going to converge towards the optimal frequencies lambda star. And this result is actually more robust than the first in the sense that it holds starting from any prior belief. Okay. And just to quickly demonstrate the property on this example, so here X3, recall, was a minimal spanning set. It's of size 1. And capital K in this example is 2. So there's 2 unknown states, omega and B1. So here we have that there is a minimal spanning set of size strictly smaller than capital K, which is why this falls under the first proposition and not under the second efficient information aggregation result. Okay. So just to give you a quick idea of why these results hold, we study this object, which is essentially a normalized asymptotic variance function. I'm going to call that V star. It is defined on frequency vectors. Okay. And it has the following properties. So first, it's strictly convex in the frequency vector. And second, its unique minimum is the optimal frequency vector, lambda star, that we spent the first part of the talk characterizing. Right. Now, society's acquisitions follow a procedure much like gradient descent. So eventually, they're going to be acquiring signals that maximally reduce V star. There's a catch. Okay? It's not actually gradient descent because you're only allowed to acquire an observation of each of the available signals. So it's kind of like we're imposing a grid or a basis on top of the structure, and we're only allowing movement along that basis. Now, this restricted movement is without loss if V star is differentiable. Right? The question of whether or not the frequency vector will eventually converge to the minimum doesn't rely on the way in which you're allowed to move, because the directional derivatives can be rewritten in that case as convex combinations of your partial derivatives along these basis directions. So if you were going to converge to lambda star on the left, then you're also going to converge to lambda star under this restricted movement procedure. Okay. However, V star is not differentiable everywhere, and it's exactly these points of non-differentiability that give us our learning traps. You can see that in this example we've been looking at. Consider the frequency vector lambda is equal to 0, 0, 1. That corresponds to all of your attention being on this third signal, X3. And you can just convince yourself that shifting a little bit of weight away from X3 towards X2, or away from X3 towards X1, both of those are actually going to move you up the curve in the sense that they're going to increase your uncertainty about omega. Okay, but if you were allowed to move a little bit of weight from X3 simultaneously towards X1 and X2, then you would move down the curve. Okay, so that's exactly a failure of differentiability. And we show that a sufficient condition for differentiability is that these frequency vectors have at least capital K non-zero coordinates. So that's why that's going to be related to the guarantee of efficient information aggregation. Okay, so this is something I'm really not going to spend essentially any time on in the talk, but in the paper we look at information interventions. Right, so the idea is, look, we have society sometimes acquiring the wrong kinds of information. Is there anything that a policymaker could do to encourage them towards the better sources? And we consider 2 interventions. So one, releasing free information about the confounding terms. You can think about this as like NSF support for methodological research. It's a research which is maybe not directly interesting, but it can be used as an intermediate step towards something else. We also look at restructuring payoffs so that each agent acquires signals for many periods and then takes an action. So you can think about this as lab structures, where a researcher is allowed to direct the attention of many people at once. And we provide conditions under which these 2 interventions do end up improving the long-run speed of learning. Okay, so just to conclude, what I've shown you here is a model of learning from overabundant information. Okay, in these cases, the choice of kind of information generates an externality for other agents. And the failure to internalize this externality can result in inefficient information aggregation. Okay, but it need not. Whether or not it does depends on the whole set of correlations across the sources, and our main results separate these cases where we have efficient aggregation and these cases in which we don't. Okay, so thank you for listening, despite lunch being just around the corner.